got 9 problems on it. You shouldn't have any trouble with them, but if you do, refer to what I'm going to talk to you about right now, because there's some things that you're going to need to remember how to do from algebra. So these are the kind of things that you're going to need to remember how to do. You need to remember that 1 over x to some power can be rewritten without it being a fraction as simply x to the negative, I'm sorry, that's supposed to be an x to the negative n power. You can bring something up out of the denominator of a fraction by making its power be negative. Okay? You'll need to remember that the root of a function, which I'm going to put this here as x to the n, and this is going to be the d for the index, that you can rewrite that root as x to the n over d power, where the index d is the denominator of the fraction, and if there is a power underneath the radical, then it becomes the numerator of the fraction. You need to remember those 2 things. Okay? Those are both very important things. You're also going to need to remember how to actually multiply out binomials like x plus a times x minus b would be x squared plus ax minus bx minus a times b, whatever a and b are the numbers. You'll need to remember how to multiply out 2 polynomials, and we did that last time too. And you need, of course, to remember how to collect like terms, which we've practiced that a lot. The hardest thing for most people is going to be when we get to the section on chain rule is remembering what a composite function is. If you have a composite function, a lot of times you'll see it written this way. I don't like that notation, but sometimes you do see it that way. The way that you're going to see it more in calculus when we come to section 3, which is about what's called the chain rule, is you'll need to remember that that stands for the function of g of x, where g has an input x, and once you put that into x, then you let f operate on it. For example, if f of x was the square root of x squared plus 3, and g of x was 2 times x, okay? The way that you calculate f of g of x is first you calculate g of x, which is 2x, and then you take that 2x and you plug it into the function f in place of the x. So then f of g of x is the square root, because that's what f does, of the quantity 2x squared and add 3. And what you'll hear me refer to this as when we get to section 3, which we hopefully will get to it tonight, you'll hear me refer to f as the outside function. Because f is the part of the function that's doing this. Okay? And then I will refer to g as the inside function. So this is what's going to go inside f of x. Okay? And when we do chain rule, it's important to be able to distinguish between which is the inside, which is the outside. Not necessarily how to simplify it, because you won't necessarily need to simplify f of g of x. You just need to know what goes on the inside and what was on the outside part. And when we get to section 3, you'll understand why that's important. It'll make more sense to you in context. Excuse me. So we're going to start out taking derivatives again. You're saying, oh no, I just did that. I don't want to do that again. But Little recap of why we even need to do this. What we found is the derivative is a useful tool because we use it to describe the rate of change or the slope of a curve. And one of the applications that we used it for was to find velocity, what we normally call speed in miles per hour or feet per second or something like that. It's a rate of change of a person or a car or something changing distance over a certain amount of time. However, as you learned, and hated every minute of it, and I don't blame you because I did too when I was in your place, doing it with the definition, the four-step process, it's not fun. It's ugly, it's long, it's tedious, and it's frustrating. But that is how you learn what the derivative means. That was what Chapter 11 was all about, and it was so difficult because it's a brand new concept for you. But now you're going to have a shorter way to take a derivative without using the definition. So in order to take full power of it, we're going to have faster ways to calculate that derivative, and it's a much easier way. So here we go. First of all, I need you to understand that all of these mean exactly the same thing. It's just different ways of saying the slope of some function x. That's really all it is. I don't use this notation very often. It gets to be awkward. This is a little better, but actually the two that I will use the most often is this notation or this notation. This is read as f prime of x, and it means the derivative of the function x. This is read as the differential notation for the derivative. It's the differential of y with respect to x, or the derivative of y with respect to x. And it will help us to understand that more because those of you that have a TI-84 calculator, when we do n derivative on your calculator, that's choice number 8 on your math menu, on the TI-84, the first thing you're going to see is d over d in a box. And then in a set of parentheses, you're going to need to enter in whatever f of x is, the function. And then on the outside, there's going to be another little box over here, but it's going to say in front of it, x equals, and you're going to fill in that box. So what's going in this box is going to be the variable you're taking with respect to, which would be your x. What's going to go here is your function f of x, and then x here is going to be some number. So I'm going to be showing you how to use your calculator to actually verify the numerical value of a derivative, even though you'll take it with a formula and compare the two. And sometimes if all you need to know is the value of the derivative at some specific value of x, and you've got the function, you can plug it straight into your calculator and it will give you the value of the derivative. And that's okay. Because the number itself isn't of any value to it. What the value comes from is the context it's placed in. So we're going to have to be learning how to answer word problems with a correct sentence. So here's the first set of rules, and these are all really straightforward. Basically, this says that for any constant, k just represents some number. If k is a number, any real number, and f of x is equal to k, if f of x is equal to some constant number, then the derivative of f of x, which is f prime of x, is simply 0. Always. The derivative of a function that is equal to a constant is always 0, which means that part of that function, if it's a constant, that will disappear in the derivative. And this should make sense to you because, for example, I'll show you a picture of one. Remember, derivative represents the slope at a point. And if your function, let's say this is 3, for example, that means we have the function y equals 3. Y equals 3 is a horizontal line. what's the slope of a horizontal line? It's 0. So it makes sense that the derivative of a constant would be 0 because that's the slope of the horizontal line. So our first three examples are really, really quick. If f of x equals 0, 0 is a constant, then f prime of x is f prime of 0, which is 0. If h of t is equal to pi, pi is not a variable. Pi is just a number. So since pi is just a number, it represents the ratio of a circle and its circle's circumference and its diameter. It's just a number. And since it's just a number, the derivative of pi is 0. If y equals 2 raised to the third power, 2 raised to the third power always gives you the same answer. It's 8. And the derivative of 8 is 0. The next one we're going to talk about is how a power function works. For example, looking at the powers of x. If f of x is equal to x, in reality, the power of that x is 1. And also in reality, even though we never write it down, the coefficient of that x is 1. In fact, the coefficient of all of these x's is 1. So when we take this derivative, what you're going to see happens is that when you have the derivative of a variable raised to a power, and you're taking the derivative with respect to that variable, all you're going to do is drop the power down in front of the variable and use it as a multiplier. So in this case, that 1 is going to come down in front of that 1x. And then we're going to take that power, which was 1, and we're going to subtract 1 from it. So the derivative of 1x to the first power is 1 times 1x raised to the first power, and the first power is going to be subtracted by 1, which turns out to be 1x to the 0. And what's x to the 0? What's its value? What's anything to the 0 power? It's 1. You can check that out on your calculator. Put in any number you want to, any expression you want to, raise it to the 0 power, and it is 1. So that's really 1 times 1, and that's just 1. If we have x to the second power, we're going to do the same thing. We're going to bring the 2 down in front, times that 1, which leaves us with 2. The power originally was 2, but now we're going to subtract 1 from that 2. So the new power becomes 1. So the derivative of 1 times x squared is 2 times 1x to the 2 minus 1, which is 2x to the first power, and we'll usually just write that simply as 2x because we know we don't need that 1 for a power. It's understood to be there. But that pattern continues. Here we have the derivative of x to the third, or 1x to the third. So what happens is the 3 comes down in front, and 3 times 1 is 3, times x to the 3 minus 1, and 3 minus 1 is 2. With 4, it works the same way. The 4 comes down in front, 4 times x to the 4 minus 1, but 4 minus 1 is 3. If you have a negative power, that doesn't change anything. Negative 1 times 1x is negative 1, times x to the negative 1 minus 1 is negative 2. And negative x to the negative 2 is the same thing as negative 1 over x squared, but a lot of times we'll just leave it this way. You never thought you'd hear an algebra teacher say that. They always said, oh, you can't have negative powers. Yes, you can. We need negative powers in calculus. They're very useful. They make things easier to work with. So I would accept either this answer or this answer. And as we go along, I'll tell you different places where, okay, this is the calculus. These two steps were the calculus. Now, in my math lab, they may go on and tell you that there's all of these steps. But you did the calculus when you got here. Everything they're doing after that is just algebra. And if you type in the first step, the completed calculus step, correctly, it will count it right. You don't necessarily have to do all the simplifying for even my math lab to count it right, because it knows when expressions are equivalent to one another. If the power is a fraction, that changes nothing. The power here is 1/2. So you bring that 1/2 down in front and multiply by it, and then you reduce that 1/2 power by 1, and 1/2 minus 1 is negative 1/2. So your answer is 1/2 times x to the negative 1/2 power, or you can bring the x to the negative 1/2 back down to the denominator and call it 1 over 2x to the 1/2. And some people even go so far as saying it's 1 over 2 times the square root of x, and that's fine too. Those are all the same thing. I'm happy if you leave it at this. The others are just algebraic manipulation. Okay? I want you to know how to do the calculus. We'll do algebra when we have to. If we don't have to, then we don't have to, and I won't count off if you don't. So basically, this is just a summary of what the power rule tells us. The power rule says that if f of x is the variable x raised to any power, regardless of what that power is, any power that's any real number, then the derivative of x raised to that power is in the power, dropped down in front, times that little variable x, and then reduce the power by 1. This is your memory word, drop and reduce. Drop it in front, reduce it by 1. That's how you remember how to do it. So here's our first example. We have f of x is equal to x to the 6th. F prime of x is equal to, bring the 6 down in front, times x, and reduce the power by 1, which means that your final answer is 6x to the 5th power. Okay? Don't you wish you'd known that in Chapter 11? Because it's the same answer you would have gotten. If y equals t, this time we don't have x as our variable. Our independent variable is t. If y equals t, we know that that's the same as t to the first. So dy dt, which is the derivative of y with respect to t, is 1 times t to the 1 minus 1, which is 1 times t to the 0 power. And since t to the 0 power is 1, then that's just 1. And just to keep connecting up the idea of slope in your mind, this is equivalent to the line y equals x. Okay? Y equals x says basically for every value of x, y has the same value. So if x is 1, y is 1. If x is 2, y is 2. If x is 0, y is 0. If x is negative 1, y is negative 1. And when you connect up the points of y equals x, it looks just like that. What's the slope of that line? 1. Up 1 over 1. Up 1 over 1. Up 1 over 1. So the slope is 1. And that's why your derivative then is 1. because the derivative found the slope of the line. Is this making sense to everybody? Okay, here's where we run into problems because we didn't have any rules about fractions. But we do have a rule that says that you can convert y into an expression where it's 1 times x to the minus 3 power rather than 1 over x to the third. That's the same thing. So that means if we want to find dy dx, we bring that negative 3 down in front. And then we subtract 1 from that power. And negative 3 times 1 is negative 3 times x to the negative 3 minus 1 is negative 4. At that point, your calculus is done. Yes, it is equivalent to saying negative 3 over x to the 4th power. But you don't have to say that the answer is negative 3 over x to the 4th power. This means the same thing. So you can actually stop there. Your calculus at that point is finished. Because you have to be able to bring it down and use it so the x to the 3rd power is in the denominator. And our power rule only applies when the power is in the numerator. It doesn't apply to rational expressions. Y'all bear with me while I hunt for where that microphone is. I bet it went under there. Oh, there it is. I need one with a headset. This one doesn't work. Okay. How about I just lay it there? That seems to work. Okay. The function here is x to the 4/3 power. Okay? This simply says take the derivative with respect to x. So the derivative with respect to x of the function x to the 4/3 power says that I bring the power down in front. I keep the x where it is, and then I subtract 1 from the 4/3 power. And 4/3 minus 1 is negative 1/3. And you will want to change these back to a fraction so that you'll be sure that you got it right. So this is going to be 4/3 times x to the 1/3 power. That power is still positive. And there's nothing at all wrong with that. Just be sure when you type it into MyMathLab that you actually have this as a fraction and you have this as a fraction. Okay? Any questions so far? Okay, we'll keep going. Here again, I don't see a power. Not immediately. I have y equals the square root of z. The independent variable is z. I need to be able to write that square root as a power to be able to use the rule because I only have one rule right now. So dy over dz can't be found until I rewrite y as z to the 1/2 power because the square root of z and z to the 1/2 power are the same thing. So then now I can find dy dz. I bring the power in front times z to the 1/2 minus 1 which is 1/2 times z, and 1/2 minus 1 is negative 1/2. And once again, that's a perfectly legal, nice expression. It doesn't have to be changed. It doesn't have to be rewritten. If you want to, or if it makes it easier to do something with it, you can put the z back in the denominator, because that's z to the negative 1/2, and make it positive. Or you can even make it back into a radical. But this is the calculus. This is algebra. This is required. This is not. Okay? Now, if I go too fast, let me know. Miles, you do know that you can print your PowerPoints off, your notes off, and show me. You just didn't have time? Okay. I was just thinking that'd save you time taking notes. Okay, that's fine. They're in Shovie. The notes are in Shovie. Okay, I will check. I thought that I had opened them up in Shovie, but I may have forgotten to unlock yours. But I will do that before I leave tonight. Yeah, they are also in, I print the Word versions of them in D2L. Okay, this rule looks like it's telling you something really cool and really necessary and, really confusing. It's not. We could actually do without this rule as far as I'm concerned, because I kind of ignore it. But I will show you how it works. Nothing's really changed here. If y equals 8 times x to the 4th, what that rule says that you can do is, if you're trying to find dy dx, or if you're trying to find y prime, the first thing that you can do is you can pull that 8 out in front before you find the derivative. And then you find the derivative of x to the 4th, which is 4 times x to the 4 minus 1, which turns out to be 32 x to the 3rd power. But I find that to be an irrelevant step, because all you really need to do is exactly what we've been doing. You've got 8x to the 4th power. Bring your power down in front, and then reduce your power by 1. And 4 times 8 is still 32 x to the 3rd power. And I'm all in favor of not having to rewrite it. So we okay on that one? This one works the same way. If y is negative 3/4 x raised to the 12th power, dy dx is equal to 12, because you bring your power down in front, times negative 3 over 4 times x to the 12 minus 1. And if you don't want to multiply the fractions and take a chance on getting that part wrong, you can always use your calculator. 12 times negative 3 divided by 4, and have it give it to you as a fraction just in case it doesn't come out even. It comes out to be negative 9. And then x is to the 11th power. You reduce your power by 1. Okay? Now, if you're pretty good at doing fraction arithmetic, you could have gone straight there without your calculator by saying 4 goes into 12 3 times. 3 times negative 3 is negative 9. So I'm not telling you have to use the calculator. I'm just saying you can if you're a fraction arithmetic's a little rusty. Okay? Yeah, don't forget your sign changing. You do have to hang on to that sign, so watch those signs. That's the number one cause of problems with this, is forgetting the signs. The derivative with respect to t of negative 8t. What's the power on t? 1. So d with respect to t of negative 8t is 1 times negative 8 t to the 1 minus 1. And when you simplify that, 1 minus 1 is 0, and t to the 0 is equal to 1, so it kind of disappears, and 1 times negative 8 is simply negative 8. Sometimes the notation looks worse than what the problem actually is. This one has a fraction power. Once again, don't let the fraction throw you. The derivative with respect to p. Bring the 3 halves down in front, times 10p to the 3 halves minus 1. 3 halves times 10, 2 goes into 10 5 times, so that's 3 times 5 gives us 15. P, 3 halves minus 1 is 1 half. So the derivative of that function with respect to p was 15p to the 1 half power. And then this is our last example before we go adding another little twist to it. 6 over x. I can't handle having fractions. I don't have a rule for fractions here. I don't have a rule about putting the variable in the denominator. So what I do is I rewrite y as 6 times x to the negative 1 power, which means then that dy dx is negative 1, the power, times 6x to the negative 1 minus 1, which makes it negative 6x to the negative 2. Think you understand the power rule now? Okay. This next slide looks like one of the others that we looked at a minute ago. It looks like it's saying something really complicated, but it really isn't. So I'm going to tell you what it says in English. It says if you've got a function that's a bunch of terms added and subtracted together, a polynomial function of some sort, the way that you take the derivative is you take the derivative of each term, and you keep the addition or subtraction operator that goes in between them. So the first thing we're going to do is just look at an example so you see how this works, and you'll see that it really isn't hard at all. This one has 2 terms. I need to find the derivative of y. That means I need to find either dy dx or y prime. And all I'm going to do that is initially I'm going to ignore that second term. I'm only going to look at 6x to the third. What's the derivative of 6x to the third? That's exactly right. 18x squared. 3 times 6x to the 3 minus 1. 3 times 6 is 18, and 3 minus 1 is 2 for the new power. The next thing I see is a plus sign, so I keep that plus sign. I keep the arithmetic operator. And then I have 15x squared. What's the derivative of 15x squared? 30x. Bring the power down in front, times 15x, reduce the power by 1. 2 times 15 is 30, x to the 2 minus 1 is x, because it's x to the first. You don't have to do anything else to that. You're finished. Okay? This one is more of the same. We're just mixing up some of the rules that we used before. First thing we're going to do is we're going to rewrite P of t. P of t is 12t to the 4th minus 6 times t to the 1/2, because the square root of t is t to the 1/2, plus 5 times t to the negative 1. Then we're going to do a derivative of each term, one term at a time. So the derivative of 12t to the 4th is 48t cubed. And then I need subtraction because the next term is subtracted. So minus, what's the derivative of 6t to the 1/2? Okay, 3t to the negative 1/2. And then the next operator is addition, so I'll add. And the derivative of 5t to the negative 1 is negative 5t to the negative 2. Now, if instead of writing plus a negative and putting that in parentheses, if you didn't want to do that, you could have simply said, well, this is 48t cubed minus 3t to the negative 1/2 minus 5t to the negative 2. But you don't have to. Okay? Any questions so far? Okay, now this one looks pretty terrible. It really does. So the technique I'm going to show you is one that we're going to use quite a bit, because it'll make it simpler for us to work with if we do something called decomposing that fraction into two fractions. Okay? This is actually the result of having added two terms together that had a common denominator of x. So what we're going to do is we're going to undo the common denominator and separate it back out into two pieces. And the way that we're going to do that is actually pretty easy. We're going to take the first term, which is x cubed, and we're going to take the second term, which is 3 times the square root of x, and we're going to separate those two and put an x under each one of those. Then we can simplify the first one, because that's x to the third over x to the first, and so that's x squared. This one, it'll be easier if I simplify it, if I change this so that I have x to the 1/2 power, because this is x to the first power. So then what I've got there is plus 3x to the 1/2 minus 1 power, because that's what you do when you have same bases dividing into each other with different powers, is you take the top power minus the bottom power. So that means this function really looks like this. X squared plus 3x, and 1/2 minus 1 is negative 1/2. So that's really what I want to take the derivative of now. So now that I'm ready to take the derivative, the derivative of x squared is 2x, or 2x to the first, plus negative 1/2 times 3 is negative 3/2, times x, negative 1/2 minus 1, negative 3/2. And there again, if you want to take away the parentheses, you don't want to have to deal with them, then you say 2x minus 3/2 x to the negative 3/2 power. But either one of those is correct. Remember, I'm only doing the calculus. I'm not going to do all the algebraic simplification that comes after the calculus step. Okay? A couple more examples. This one doesn't look like there's anything we can do with it, because we haven't dealt with anything that has parentheses around two terms. This actually is a problem that we're going to come back and revisit when we get to the section on chain rule. We're also going to revisit this problem when we get to the next section on what's called a product rule. There's 3 ways to do this problem. But we can do this problem right now. We just have to do a little algebra first. 4x squared minus 3x in parentheses squared actually means (4x squared minus 3x) times itself. So we can multiply it out. 4x squared times 4x squared minus 3x times 4x squared minus this 3x times 4x squared minus 3x times minus 3x. So f of x is actually equivalent to 16x squared minus 12x to the third minus another 12x to the third plus negative times negative is positive 9x squared. And then we'll combine the two middle terms because they are like terms. Oh, it's to the fourth, thank you. 16x to the fourth, forgot to add my powers. So 16x to the fourth minus 12 and minus 12 gives me negative 24x to the third plus 9x squared. And now it's not at all hard to take the derivative of that. You can take the derivative of this faster than you could do all the rest of that stuff. So there's all your steps, and you may have done some of that in your head and already have the answer. So the derivative is 64x to the third minus 72x squared plus 18x. Okay? You can use the graphing calculator, and what I'm showing you here is different from what you have in your notes, because in your notes I have you do it by the graph. But you can verify even an algebraic derivative by using nderiv. If you do it using the graph, what you do is you put in y1 the original function. And then you put in y2 the derivative of that function. And then you put in y3 nderiv of y1, or type in the function, with respect to x for all values of x. And then what you're going to do is you're going to turn this function off, because that function really doesn't help you. So you're going to leave on y2 and y3, and what you're going to see is you're going to see one single graph. But what this shows you is that if you do this, you put the derivative in y1 and you put what you came up with in y2, and then you set your table up and let it go on auto on both, you see that all of your x and y values are identical. Okay? So you can always check if you need to. Any questions? Okay, I've got a couple of examples of application problems, but I'm going to give you all a short break. Let you take a break, stretch your legs, get a drink of water, and then we'll come back and do those, and then work on the next section, because this is really the end of this one. Take about 10 minutes. Okay, there it goes. Okay, let's get started back. We've got a couple application problems, and then we're going to go on and talk about something called the product and the quotient rule tonight. So here's our first application problem. And here again, I told you that things that I want you to type in your mind are certain words. This is talking about marginal cost. And anytime you see the word marginal anything, marginal cost, marginal revenue, marginal profit, anything like that, marginal means slope or rate of change. Okay? And when we're talking about a slope or a rate of change, what we're talking about is a derivative. So now not only do we take the derivative, which fortunately we don't have to use that long method for, we've got shorter processes now, but we're going to have to actually plug in a number and explain what that rate of change or that marginal cost means in terms of cost. So we have here a cost function, and this cost function is the cost in hundreds of dollars. We have to pay attention to our units, so it's in hundreds of dollars to produce X thousand barrels of a beverage. So we need to pay attention to those units. And when it says find the derivative of cost when X equals 5, the actual answer we're going to come up with is going to say the cost of producing the beverage is, and this is going to be either increasing or decreasing. We have to see what the derivative is first at that point. So there's going to be increasing if it's positive or decreasing if it's negative, but it is so many $100 per 1,000 beverages at a production level of 5,000 barrels. And we know it's 5,000 barrels because X is 5, and X represents the number of thousands of barrels. So we need to take all of that into account when we answer this question. Now, we can answer it in short order using the calculator. We do not actually have to calculate the derivative. But you should be able to calculate that derivative because it's actually pretty easy to calculate. So what we want to do is we grab the calculator and we turn it on. And we have to enter in the function, which is an easy function to enter in. So we're going to go math, scroll down and select option number 8, in deriv. And at this point, my screen on the 83, excuse me, thank you. My screen and yours don't look exactly alike. So those of you that have the 84, your first entry is going to be X. Okay? Then you're going to enter the function. For those of us that have the 83 or the 83 plus, we're going to enter the function first, which is 4x squared plus 100x plus 500. And then we're going to put in a comma. Now, the 84s don't need that comma. The 84s have X in the first box, then you enter in the function in the parentheses, and then in the very last box, you enter the number 5. But for us, we enter the function, we type an X, we type a comma, and then the numerical value we want for X is 5. Remember, the interpretation comes after we actually get the number. And we hit enter. And it says it's 140. And that's positive. So for that reason, the cost of producing the beverage is increasing $140 per 1,000 beverages at a production level of 5,000 barrels. Now, I'm going to move the calculator out of the way for a little bit because, you know, talking about 140, that's not something we usually do. So a better way, even though this is perfectly correct, this is correct, another way we can say that is the cost of production is increasing by, let's see, 140 hundred is 14,000. 140,000, yeah. Yeah, 14,000 is $14,000 per 1,000 beverages. At 5,000 barrels. And this looks a little bit more like a number that we're used to seeing. But this illustrates why it's so important to pay attention to what the problem says the units are. Now, we got the answer strictly from the calculator because we had a number for X. And the calculator will always give us a numerical value unless it's not defined at that value. We could also take that derivative. The derivative of cost is C prime of X is equal to 4 times 2 is 8X to the 2 minus 1 is 8X to the first power plus 1 times 100 is 100 times X to the 1 minus 1, which is X to the 0 or 1, and the derivative of 500 is 0. So here's our entire derivative. C prime of X is 8X plus 100 $100 per 1,000 barrels. At a production level of X thousand. And if this was a problem that you had to deal with in your business career, that's the answer you're going to want to give. Your boss isn't going to want to hear, well, C prime of X is 140. Your boss is going to say, what? What are you talking about? So you need to know how to interpret that, and this is the interpretation, okay? And hopefully you can see easily that 8 times 5 is 40, and 40 plus 100 is 140. So doing it either way, using the end-derivative method or actually taking the derivative and plugging in the number, both of those are fine.
How'd you get rid of 500 again? Like in the 4x squared plus 100x plus 500. How did
the derivative of a constant is 0. Okay? So any constant that's at the end of your function, it just drops away. Okay? Just disappears. Now, the next part of this problem, this is why end-deriv is such a nice thing to have, as well as having your actual function. The next part of this problem, and I showed you here that you can actually do it using end-deriv, is that in part B, they're going to ask us about a different production level. In part B, they're going to ask us about a production level of 30,000 barrels. So C prime of 30,000 barrels is going to be 8x to the first plus 100, which is going to be 8 times 30 plus 100. And 8 times 30 last time I checked was 240. So that's $340 per 1,000 barrels. And you would write the same sentence you did before. And then you can also check your problem using end-deriv like we did before. The only thing that you need to change is the number at the end. And then again, you interpret. So at 30,000 barrels production level, the cost of the beverage is, again, increasing by, let's see, 300 and 4,000 is $34,000 per 1,000 barrels. Okay? So some important things to take notice of here is when you're answering this kind of question, be sure, number one, that you're talking about a derivative, therefore you're talking about a rate of change, and your rate of change is going to require units for your input variable and for your output variable. So that's going to be that $3,400 per 1,000 barrels, and that word per is key. You have to have that word per because it's a rate of change. And the other key is that since it's an instantaneous rate of production, the correct verb is it is increasing. If we said between 5,000 and 30,000 barrels, then we would say that the rate of production, the average rate of production between 5,000 and 30,000 was so many hundred or so many $1,000s per barrel. Okay, because that's over an interval. Because this is a single point in time, then the correct verb is it is increasing, or had it been negative, it is decreasing. Okay? And there again, I showed you how you can do it on the calculator. And that is, it's in the PowerPoint that I put up for you too. Now the next thing that we're going to talk about is demand functions. And I think most of y'all at this point either have taken or are in the midst of taking economics courses. Both macro and micro, one or the other or both. And demand functions, you know that the quantity of something demanded depends upon what price that's being asked for it. We have a supply function, which is the function at which the manufacturer is willing to produce it for a certain price. But we also have a demand function, which talks about how many people are willing to buy at that price. And of course, as the price increases, the suppliers are willing to make more and more and more. But as the price increases, the consumers are willing to spend and buy less and less and less of it. Okay? Right now, we're talking about a demand function here, and a demand function is important because demand actually leads to our revenue function. And keep in mind, there's a difference between revenue, which is simply money you're taking in, and profit, which is the money you have left over after you pay the bills. Okay, so we need to talk about how you make revenue functions. And the demand function, the way to keep this in mind, because I didn't get to pick the variables. You're used to in algebra and math classes that the variables are X and Y. Okay, maybe they're S and T or something, but they're usually X and Y. And then all of a sudden somebody pops up and says D and Q and P, and you're saying, what? Why? Think of P as price. Okay? P is always the price. It's always money. Q always stands for quantity. How many? That's why they chose Q. And the price depends on the quantity demanded. Sometimes the price will go up and the demand will also go up, but sometimes the price will go up and the demand will decrease. So the quantity demanded depends a lot on the price and vice versa. The total revenue is always going to be related to the price and the demand. It has to be the combination of the two. Because revenue, the amount of money you take in for selling Q items, is always going to be the number of items times the price per item. And when you keep in mind that Q stands for how many you sold, and P stands for the price of each item, that makes your revenue equation make sense with P and Q. But since we know that the price is actually a function of the demand, then we can make our revenue equation strictly in terms of the quantity, because the quantity is going to determine what the value of D is. So this is the quantity demanded times the price that quantity warrants. So when we do this next problem, we have to keep in mind that this is how you calculate revenue if you've got demand. So here we've got a demand function. It says the demand function in dollars, we always pay attention to the units, so the demand is in dollars. And that makes sense because it's price. Price depends on demand and the price is in dollars. Is 50,000 minus the quantity demanded, all divided by 25,000. And this is only good on the interval where Q is between 0 and 50,000 inclusive. We don't know what happens to demand after the quantity 50,000. We don't know anything about that. Okay? And remember, Q is in where Q actually is in tens of thousands of units. So we have to pay attention to that too. So if it says Q is equal to 5, then that means 5 times 10 is 50,000 units. And we're somewhere in our interval at that point. So Q itself can go anywhere from 0 to 50,000, but then whatever Q is going to be multiplied by 10,000 because Q represents 10,000 units. So that's our demand function, and we want to talk about marginal revenue. Okay? And there's that word marginal again. Marginal means the rate of change of revenue. And the first thing we're going to have for this is we're going to have a revenue equation. So our revenue equation is dependent upon the quantity, Q 10,000s, and the price, but the price at that quantity is given by this. So there's our revenue equation, but it's not in simplest form. We need to simplify it because, first of all, we haven't studied the product rule yet, and this is a product. And we still don't have anything that we can do with fractions. All we can deal with is powers. So what we're going to do first is we're going to multiply Q times the numerator, because remember, this is like Q over 1. So 50,000 times Q minus Q times Q is Q squared. And actually, both of those terms are over 25,000. But it would be easier if we could split this up into two terms. So I'm going to do the same thing we did earlier. I'm going to take that joined fraction and break it back apart into the difference of two fractions. And then I'm going to try to simplify it because I know I've got to do calculus on it. And all those zeros are kind of a pain. So 50,000 over 25,000 is the same as 50 over 25, which is the same as 2. So that's 2Q. And Q squared over 25,000 would be the same thing as Q times 1 over 25,000. Which comes out to be 4e negative 5, which is 4 times 10 to the negative 5 power. And what that negative 5 means is that we need to move the decimal 5 places. Which direction? To the left, because this is a very small number. Negative exponents mean we move the decimal left. So that's going to be minus 0.1234, and then 4, Q squared. So there's a nice simple revenue equation that came from all of this. Algebra does make your life easier. It just doesn't necessarily have to take place after the calculus does. We're going to use it to make our life easier to do the calculus. Okay? So this is our revenue equation. And it, again, is only good as long as Q stays between 0 and 50,000. And Q represents 10,000 each. So now that we have a simpler equation, we could just go straight, if we had the number, we could go straight on to in deriv and be done with it. But for right now, the only thing we have is that we have the revenue equation, and we know we need marginal revenue up here. So what we want to find is R prime of Q. And R prime of 2Q is just 2, because 1 times 2 is 2, and Q to the 1 minus 1 is Q to the 0, which is 1. So the first term's derivative is just 2. And the second term is 2 times 0.00004, which is 0.00008 Q. So there is our marginal revenue. And this is the rate of change, and it's in dollars per Q 10,000 units. And I think I may have lost one of my pages, so I'm going to have to look and see what we're looking for. What does your problem say that Q is supposed to be that we're looking? $10,000 units? Okay. So Q, does it say Q equals 10,000? Oh, when Q equals 10,000 units. Okay. Sorry, I totally overlooked the word when. Thank you. So that means we're going to plug in 10,000. I kept referring to that as per 10,000 units, but Q actually represents 1,000 units then. Or units, not 10,000 units. So for 10,000 units, R prime of 10,000, this is a pretty simple equation to substitute into. 2 minus 0.00008 times 10,000 dollars per unit, because we have a value now for Q. So we need to do a little arithmetic. And we get 1.2. But 1.2 is in dollars. So that's $1.20 per unit. Okay? And I put demanded, but you could also say are produced and sold, because that's what demand is. It's production and then selling that many. When 10,000 units are demanded, the revenue is increasing by $1.20 per additional unit. So if this was 10,000 units, then the 10,000 first unit would cost $1.20. Or it would bring in, I'm sorry, it wouldn't cost $1.20. It would bring in it would cost the consumer $1.20, but it would bring in $1.20 revenue to you. Okay? And this graph, even though I wouldn't necessarily expect you to make it, this graph basically shows that that's the case. Because this is your price equation, but this is your change in revenue equation. This is your marginal revenue equation. So your marginal revenue at 10,000 units is $1.20. But notice that the price is $1.60 each at 10,000. So remember, this is your revenue. This is the price that people will pay for it. And then the next one shows us the revenue function. So when you look at this is your revenue function, and this is the function that I changed this into that decimal. That's what that is. But this is the actual revenue equation, not the marginal revenue, but the revenue equation. So what does that tell you about your revenue? Is your revenue going to continue to increase forever? What's happening to your revenue about here? That's all the money you're going to make. Are you not going to sell anymore? Well, your revenue's not zero at that point, but you've maximized your revenue. You're not going to keep making more and more revenue. What's going to happen is you've saturated your market. You saturated it to the point that people are no longer interested in purchasing them the way they were here. It's a fidget spinner. There you go. I was wondering if anybody was going to remember about the fidget spinners from last semester. At this point, it was about Christmas time, and the fidget spinners had hit their peak. And it's not that nobody buys them anymore, but they're not paying as much for them, and your revenue is decreasing and decreasing and decreasing. And if you sell or you can't continue making them past 50,000 of them, well, your revenue is negative, and that's because you're having to store fidget spinners nobody wants. Okay? So this, these things should make sense to you. Now, sometimes economists will rewrite this equation, and I'm just going to mention this. This is not something that's really that big a deal. But sometimes they do rewrite that equation, and they give the quantity in terms of the price. And that's because they are very much interrelated. Your quantity is a function of the price you charge, the price that's charged. So, excuse me. We could have actually done this problem exactly the same way we did it a few minutes ago. We could have taken P times this function and gotten another revenue equation. And the new revenue equation in terms of P would have been 50,000 P minus 25,000 P squared. We would have still gotten the same derivative. We would have still come out with the same price for the marginal revenue. We would have still come out with $1.60 per additional unit. Okay? So you can actually write those either way. So revenue can be a function of the price, but revenue can also be a function of the demand because they're all interrelated. So continuing on with that sort of example, let's talk about marginal profit. Revenue's nice, but profit's nicer because that's the money we get to keep. Suppose the cost function for that product in example 7, where Q was between 0 and 50,000. Suppose the cost was 2,100 plus 0.25 times Q. Now think about what that tells you. Your fixed cost is $2,100. Okay? And then for every additional unit you make, it's another 25 cents, basically, to make it. Find the marginal profit. Okay, you've got to remember that profit is always equal to revenue minus cost. So we would take our revenue equation, and we would want the revenue equation that's in terms of quantity. So that means we would go back to this equation. And I'm not using that 1 over 25,000. I'm going to use the decimal. And then I'm going to subtract the cost from that. So your profit function for Q units is going to be 2Q minus 0.0004 Q squared minus 2,100 minus 0.25Q, which I'm going to bring over here under the Q term. So that means our profit function is negative 0.00004 Q squared plus 1.75 Q from that minus 2,100. And we would like to find the marginal profit, or the rate of change of profit, when we make 15,000 units. So Q is going to be 15,000. Now we can take the derivative. Since we're looking for marginal profit, we can take the derivative. And that's not hard to take. It just involves a lot of decimals. Or since it's a numerical derivative, we can take it this way. And of course, we'll have to use X in place of Q. And it says that that's 55 cents. And it is positive. So our interpretation of that is that at 15,000 units produced and sold, profit is increasing by 55 cents per unit. So at 1,500 units, you're still increasing your profit. Your profit's still building. It's still growing. You not only still have profit, but your profit is getting larger. It's growing larger. Okay? And then Part B says to find the marginal profit from production of these numbers of units. So we want to find the profit from 21,875 units. So that means all we're really going to do is we're going to change that 15,000 to 21,875. What happened? No profit. No profit, or profit's not changing. Okay? 0 means your profit has reached a maximum. Think back about this profit equation. Remember, we didn't take the derivative except numerically. We didn't actually come up with the derivative of this profit equation. Okay? But what does that equation look like? What kind of graph does that equation make? What does this tell you that equation looks like? It's a parabola. What does this tell you about the way that parabola opens? It opens down. So, you remember when I pointed to that graph a second ago and I said at some point your revenue is going to slow down? Well, when your revenue slows down, sooner or later your profit's going to die. So what this means is my profit at those units my actual profit is $17,040 and change. But that's the highest profit I'm ever going to make. I have reached the maximum profit because my profit is now not changing. It isn't increasing, but it isn't decreasing, which means it's at a maximum. Okay? So that's actually my maximum profit is $17,040. And I know that that is my maximum profit because my derivative of profit at that point at that point, my profit is neither increasing nor decreasing. Now, we'll talk a lot in Chapter 13 about how useful it is to know where your derivative is equal to 0. Because when your derivative is equal to 0, that tells you that whatever you're looking at has reached either a peak, it's maxed out, or it's reached a valley, and it's about to start climbing. Okay, and that's important to know. And you'll know that this is actually a peak because if we calculate at $25,000, because that's our next one, 25,000 units, I'm first going to calculate the profit itself. I did still make profit. My profit is still positive, but it's only $16,650. Okay? It's dropped down from that $17,000. Profit is decreasing. You're not losing money. You're just not making it hand over fist like you were. And the rate of change will show us that. So let's see my profit function. What did I do with it? It froze up for a second. Yeah, now my profit is decreasing by 25 cents per unit. Not decreasing by very much, but it is decreasing. Okay? Mm-hmm. X. Let's see.
Put X right there, right?
Mm-hmm.
And then I plug in this.
Except that it needs to be in terms of X, yes.
Yes.
Minus 2,100. And then the last one has 25,000 or whatever.
I got negative 10.9.
You're leaving out a zero. A very important zero.
That other zero.
Yeah. Yeah, because I did it 2 or 3 times when I was doing this. Count your zeros carefully. Okay? She was leaving out one of the zeros in the 00000X. She was putting a .000. Okay, it could be. It could be. That's why if you sit me up here, I'm careful. Going, because those zeros in those places can make huge differences. Okay? That's why I tell you to write down what you put in the calculator so I can check what you put in or what you said you put in and see if it matches what you should have put in or if that's what caused the problem. Well, if you get it wrong and I can see it's because you left out one of the zeros, I'm not going to count it totally wrong. You were doing the right process. I mean, I say -1, count your zeros. Your boss is the one that's going to be upset when you leave out that zero. Okay. Do y'all need another 5-minute break before we shift gears because we have one more thing to do? Okay. Let me give you 5 minutes.